Olá, boa tarde, galerinha. Bem-vindo a mais um mock class do programa My Way da EFIG em parceria com a Study Group e a Universidade de Liverpool Hope. Hoje nós vamos falar sobre o professor Kroll. Ele vai falar sobre engenharia mecatrônica, ok? Ele vai dar aí toda essa mágica que ele faz aí, muito bacana das aulas. E depois no final ele vai dar um exercício. Todos vocês já receberam o PDF com o tutorial dessa aula, então podem acessar o e-mail de vocês aí e vejam se o e-mail está certinho. Quem não recebeu pode ficar tranquilo. Peço somente que vocês, toda hora que o professor perguntar, todo mundo tá bem, galerinha? Vocês respondem e abrem o microfone e fala yes, I'm okay, I got it, só para a gente ter aí um fluxo melhor na aula, tá bom? Espero que vocês aproveitem mais uma aula dessas. O certificado vai ficar pronto assim que essa aula terminar, ok? A gente volta a se falar no final. Qualquer coisa vai mandando mensagens aqui no Zoom, ok? Thank you very much, Professor. Welcome one more day here with us.
Hello. Right. So, I take it the majority of you will know who I am now. But again, for those people who who don't, my name is Carl Myers, and I'm the engineering project tutor, for Study Group's network of international study centres in the UK. And as I've said many, many times, my academic and professional background is in the fields of civil, electrical, mechanical, electronic and robotics engineering, and also computer science. Oh, that was a bit of a mouthful. Right, okay. So, what are we going to be doing today? Right, so during this session, I'm going to give you a brief introduction of mechatronics. I know it sounds impressive. I'm going to explain to you why you should choose to study this discipline, or disciplines in this case. I will give you some examples of the careers you can pursue with a degree in mechatronics. I will only give you a couple of examples of the careers that you can actually pursue with mechatronics, essentially because I'll explain further later on, okay? And of course, the most exciting part is where we're going to together design a mechatronics system. In our friend Tinkercad, again, I'm sure you're all familiar with Tinkercad. For those who aren't, it's an online application or online platform, I should say, for teaching the basics of the product development lifecycle, which is design, simulate, and prototype. Hopefully, you've all got an account with Tinkercad now. If you haven't, I'll give you a couple of minutes at the end, and you'll be able to sign up with it then. Okay. So let me begin, and we're going to kick off with a question again. What is mechatronics? Right, okay, apart from it sounding impressive, it really is an impressive discipline to follow, or disciplines, as I said earlier, which we'll explore a little bit further in a moment. In fact, to be honest, mechatronics was my original choice for my bachelor's degree. However, I did decide to follow a different route, as I already had a lot of experience in the fields of many fields relating to mechatronics, and chose a degree that suited my desired path. Okay, which is something that all of you should be thinking about as well. Right. So, what is mechatronics? Right. The term mechatronics was first used back in 1969 in Japan, but it's only become more common in the past 20 years as traditional mechanical products became increasingly governed by electronic and computer control. So mechatronics is an entirely multidisciplinary discipline, again another mouthful, that one, which encompasses many different disciplines such as mechanical engineering, which is an extremely broad discipline that deals with the improvement and modification of mechanical components, machines and systems. Electrical engineering, which advances the fields of electricity, electromagnetism and the things that use and generate it. Electronic engineering, which is again a branch of electrical engineering associated with electronic circuits, devices, and equipment and systems that use them. Computer engineering, which is a branch of engineering that integrates multiple fields of computer science and electronic engineering required to develop computer hardware and software. And due to the above, mechatronics is an industry buzzword synonymous with robotics and electromechanical engineering. If you all or some of you attended the robotics robotics class, I was about to say webinar then, robotics class, you will notice that it's extremely similar to the robotics tutorial. Essentially, this is because robotics and mechatronics are one and the same. They are virtually exactly the same. Okay. The only difference between mechatronics and robotics is when you choose to study robotics, you can focus more on the computer science side, i.e., artificial intelligence and that sort of thing. Whereas mechatronics, you can actually move into the realms of MEMS or micro electromechanical devices, but we'll talk about them a little bit later on. Okay, so why should you choose to study mechatronics? Again, it's a multidisciplinary discipline or multidisciplinary skills. When you gain a degree in mechatronics, you're combining a broad range of skills in, as already stated, mechanical, electrical, computer science, and control systems. In essence, you're earning 3 or 4 engineering technology degrees in one. The multidisciplinary skills and knowledge you'll gain in a mechatronics engineering degree program will give you the solid base you need to solve complex engineering problems, and this will give you a big picture perspective, flexibility, and adaptability, which are all massively key components of any career, of career success. Okay, employability. Okay, again, just like all the other engineering disciplines, employability is a key reason to choose to study engineering. But with jobs in mechatronics, they are expected to grow rapidly over the next 10 years, like they have over the last 20 years. Due to the rapidly expanding technology sector, and nearly everything we use on a daily basis being a mechatronic system. Think of nearly all of your household appliances, such as washing machines, microwaves, and even your phone. They are all mechatronic systems, and this is where Sorry, I forgot to put my phone on silent. It will go off in a second. That's a proper schoolboy error by me, that one. Okay, so in your phones are mechatronic systems, or more specifically, what is contained in your phone. For example, an accelerometer. I don't know whether any of you have ever heard of an accelerometer before, but this is what your phone uses to change the orientation of the screen. So yeah, it's in portrait mode, you turn it like that, and it goes into landscape mode. Basically, an accelerometer does this, okay? So the accelerometer is known as a MEME, or MEME, or a micro electromechanical equipment. You can think of an accelerometer as a box suspended by springs on all sides. Okay, and every time you move the box or move the phone, right, the springs either stretch or compress, which in turn give different electrical signals, which are proportional to the orientation of the box. So essentially, if you move your phone from portrait to landscape, the springs on the box stretch, which gives a different signal on that line, and it signals to your phone to change the orientation of your screen. That's exactly how they work. Okay. There we go. It's extremely high paying. They're extremely high paying jobs and starting salaries with mechatronics. Again, this may not be your main reason, and it certainly wouldn't be mine. However, I was honestly shocked by the rates of pay for mechatronics engineers, and it really did make me question my choices. According to ZipRecruiter.com, entry-level mechatronics engineers earn an average of $54,500 or £44,229. Wow. And this is just a starting salary. Again, it really, really did make me question my choices. In fact, this salary will rise with experience, just like any other job. It will rise with experience, and this is reflected in the average salary for a mechatronic, for a skilled mechatronics engineer, if you want to call it that, which is $88,800 or £72,000 per year. Again, wow. These salaries, however, are well deserved, and this is due to the nature of the mechatronics degree. Therefore, professionals with mechatronics engineering technology skills are highly valued by today's rapidly innovating companies, and the salaries reflect that. It opens doors for professional advancement. I'm sure you've all heard me say this one before. So what do I mean by this? Many of the skills that mechatronics engineers and engineers of all disciplines hone on and use on a daily basis, they do open the doors for professional advancement, meaning engineers climb the professional ladder very, very, very quickly. This is because of the way mechatronics engineers and engineers of all disciplines, for that matter, are taught to think. We're taught to analyze problems. We're team players, and therefore we have excellent communication skills, and we have the ability to manage others, and we meet deadlines. And these are all skills that are hugely desirable, not just for engineering programs or engineering jobs, across all sectors. A lot of engineers move into finance or banking, basically because we're good with numbers, and the way we're taught to analyze problems. We break them down and we work the problems. A mantra that every engineer should live by, or we all do live by, is a dream written down becomes a goal broken down into steps becomes a plan backed by action becomes reality. Okay, and that's the mantra that every engineer works to. Okay, so what are the possible routes you can follow with the degree in mechatronics? Right, I have to say this is an immensely difficult task for me to give you some possible career paths in mechatronics. This isn't due to the paths being limited. It's because there are so many different careers you can pursue with a degree in mechatronics. As I've already explained, mechatronics is a completely interdisciplinary discipline. And with a mechatronics degree, you can do everything that a mechanical engineer can do, an electrical engineer can do, an electronic engineer can do. The list goes on and on and on. You can literally do anything that they can do and follow any path that they could. So it's a massively valuable degree to have, but it is a hard degree, a really difficult degree. So you've got to make sure that you know that you would like to do this degree and be passionate about it, because that will drive you through. Okay, so I thought it best to choose two paths. Okay, the first ties in with the interactive demo. Okay, so automotive manufacturing. Okay, I'll explain a little bit more about that in a second. And the second is my speciality, which is robotics. Okay, I'm sure you've all seen the robotics, or you've done the robotics class. So again, you know this is my speciality. Right. Okay, so automotive engineering. As the name suggests, automotive engineering is solely dedicated to the vehicle manufacturing industry. Due to the huge focus on environmental and safety concerns, automotive engineers must produce vehicles that are safe and have the least impact on the environment. But this must be coupled with keeping the cost down to a minimum, as to ensure that they're economical and affordable to buy. If people can't buy them, you won't make them. So you'll be out the job, essentially. Mechatronics engineers in the automotive industry are at the forefront of all aspects of the design, manufacture, and quality control of the cars they produce. For example, a traditional car was almost entirely mechanical in nature, with the engine, gearbox, drive shafts, and wheels. The only real electrical components were the windscreen wipers and the starter motor, and the lights. A modern car, however, is a purely mechatronic system. It has a myriad of sensors which warn the user of potential faults, automatic braking systems which sense an object or pedestrian in the road and brake for the driver, and driving aids such as traction control and ABS systems. This trend will continue and, moreover, will gain pace. And this specifically with the advent of cars with self-driving capabilities, such as the cars being developed by Tesla. Okay. And essentially, if you think about it, a car with self-driving capabilities, so a car that can drive around on its own, what is that? Is that a car or is that a robot? Okay. Have a little think about that one. Robotics engineering. Again, although I have a background in many disciplines, first and foremost, I am a robotics engineer. Robotics is a branch of mechanical engineering, electrical engineering, electronic engineering, and computer science. And therefore, they are purely mechatronic systems, as mechatronics is all of the above. Okay, it deals with the design, construction, operation, and application of robots, as well as computer systems for their control, sensory feedback, and information processing. Just like the other more established disciplines, there are many different paths you can take within robotics. Again, if you've attended the class on robotics, you will be familiar with some of these. Industrial robotics and automation, okay? All manufacturing processes or manufacturing companies, they are looking to automate their processes. Essentially, they want to minimize the workforce involved in the production of any of the essentially of whatever they're producing. Okay, and this will reduce the costs, improve productivity. Industrial robots do a massive amount for production or the manufacturing industry. And this is the path the majority of you will take if you choose mechatronics and move into the robotics side, or you just choose to study robotics on its own. This is the path the majority of you will take. And it will be the most lucrative path to take, i.e. you'll earn a lot of money if you move into this path. Okay, biomimetic or biocybernetic robotics. Again, you're all very familiar with this if you attended the robotics class. In simple terms, it's the copying or mimicking of biological organisms. Again, as a race, we've been doing this since the dawn of time. Okay, just think of the bird scissors and the way a bird's beak works. Assistive robotics, assistive or service robotics. Again, this is a subject where most of my research has been focused. They are developed to, as the name suggests, help people in their daily lives or provide a service such as aiding people with disabilities or collecting and sorting recyclables. The images you can see on the right show some examples of such robots. Please have a look yourself on YouTube at some of the videos by Boston Dynamics. They're truly awe-inspiring. Okay, I have actually showed you one of Atlas, which you can see just is the second image. Second image down. They're not just limited to Atlas. They've got Spot, who's now being released in Singapore at the minute. He's now enforcing social distancing. There's another one called the Sand Flea, okay, which can actually jump onto buildings. Okay, so it's only around about this size, the Sand Flea, and it can actually jump on top of a building of around about, say, around about 30 feet or what is it, about 9 meters high. Okay. So again, massively interesting. Okay. So in conclusion, choosing to study engineering of any discipline is and will continue to be the best decision you can make. It's a massive, you'll enjoy a massively varied and fulfilling career, and with the knowledge that you're going to make a difference, however large or small. Okay, so thank you all for taking the time to listen to me ramble on about this subject, and I hope it was interesting, and definitely hope it was informative. Okay, so we're going to move on to the interactive demo. Okay, something's gone wrong with my system here. So what we're going to do, we're going to design and simulate a mechatronic system, namely an automatic braking system for a car. Okay, this isn't going to be exactly the same as the automatic braking systems in the car, but it will demonstrate exactly how they work. Okay, you're going to get the opportunity to design and simulate the system using Tinkercad, our friend Tinkercad again. In the design stage, you're going to get the opportunity, obviously with me guiding you, to design the circuitry for the system using a motor that you will not be familiar with, or you will be familiar with, but you won't know you'll be familiar with it, and sensors. You will be introduced to the software design again, where the code is going to be explained and you'll be shown the different routines included in the Arduino sketch, if you don't already know them. And finally, you're going to get the opportunity to simulate how the system will work, and you're going to get to be able to debug the software within Tinkercad. Okay. I did actually have a video to show you on how the automatic braking system works, but it's not actually working at the minute. So I'll see if I can fix it for the end. Is everybody ready? Are we ready to move on? Are we ready to get going? Have you all signed into Tinkercad?
Carl, if you just can send the link on the chat
Yeah,
for the
okay.
Tinkercad, I think that's better for the students so they
Yes.
can take a look.
No problem at all.
Don't save this.
And Carl, just
Yeah.
to double check, when the student goes to Tinkercad, they must to sign as Apple account or Google account, right?
Yes. Yeah. Don't try and join the class. Essentially, if you try and join a class, I haven't actually created a class.
Okay.
So yeah,
Okay.
just do
Thank
it that
you.
way.
Então, galerinha, o professor Carl vai colocar o link aqui para vocês. Não cliquem no Join Class. Clique no link abaixo, onde você pode entrar com sua conta do Google, com sua conta Apple, ok? Pra gente não ter nenhum probleminha. Ele vai passar o link aqui agora e aí vocês já podem logar no Tinkercad. Aqueles que já estão logados, já deixam abertos aí.
You just let me know when you're ready to go, and we'll go. Okay.
Sorry, Professor, can you just copy and paste the web link?
Oh, sorry, I do apologize.
Okay. No,
that's
okay.
what I was doing.
Thank you.
And there we go. I've just pasted I've just uploaded the link to the chat box. So you can just follow that link for me. And then again, just sign in. Again, sign in with either a Google account or an Apple account. Okay. You don't have to have an Autodesk account with it. If you do sign up with an Autodesk account, you get a lot of spam off them. So I would recommend that you do it through your Google or your Apple accounts. If you've already signed in, or you're waiting for us, if you have a look at my screen now, we're on the Create New Circuits, and if you have a look at the first four images on my dashboard, you will see what's called rectifier circuits. Okay, this is a part of electrical engineering and obviously mechatronics, and it's essentially how every piece of equipment, every piece of electrical equipment, or nearly enough every piece of electrical equipment that you own works. Okay, I won't go into AC/DC theory, but essentially we use AC currents. AC current is transferred to our homes, and that's got to be rectified down to make a DC current. So it'll run all our electronic equipment, and then 4 images is essentially how it does it. Okay, so a little bit of interest for you. I find it interesting anyway. I don't know about you. Okay, are we all ready?
Okay, Professor.
Excellent, good stuff. Good stuff. Okay, so once you've signed in, you will be faced with the 3D design dashboard. Again, I'm sure you're all familiar with it now, but if you're not, the 3D design, you'll see the 3D designs button highlighted on the left-hand side. Just underneath that is the circuits button. If we just click on that, and you will be faced with the circuit design dashboard. Okay, if you just click create new designs, and eventually it will come up, and there we go, and you'll be faced with the circuit design workspace. Okay, so the first thing that we're going to, is everyone okay with that? Are we all okay? Just a quick okay from someone.
Okay.
Brilliant, good stuff. Okay, so the first thing that we're going to do, we're going to add our control board. Let's see if I can find one. There we go. I've got one here. This is the one we're going to be using today. This is the big brother of the one that we're going to be using today. Okay, so again, if you may all be familiar with this now. If you're not, it's an Arduino a development board or a microcontroller development board. Okay, if you just want to think of it as the brains of the operation, or a little mini computer, a really, really low power computer. And this in a car, there's literally hundreds and hundreds of these all around the car, and they're all controlled or by a central controller or ECU, electronic control unit, which is essentially something along them lines, which is quite a powerful little computer. Okay, right, so to add our Arduino, if we just type in the search box Arduino, which is ARDUINO. Okay, I'm almost certain that will not be different in Portuguese because it's a brand name. But if it is, could one of you give me a hand with this and let everyone know what it's called?
No, it's Arduino. That's right.
It's Arduino. Good stuff. Good stuff. Okay, so to add the Arduino, we just click on the Arduino, and we're going to move that over to our workspace. There we go, just like that. Okay, what we're going to do, we're going to add another component called a breadboard. This is definitely in Portuguese, if someone can help me out with this. So bread, I just type in B-R-E-A-D. Can someone give me a hand with this and what we need to put in Portuguese? Breadboard? Anybody?
Placa de ensaio.
There we go. Excellent. Thank you very much. Okay, so once you've typed that into the component search bar, if you just click on the small breadboard or whatever, click on the small breadboard, and we're just going to place that just on the end of the on the Arduino like that. Okay, again, you'll probably all be familiar with our breadboards now. If you are not, it's something that we use. Electrical engineers, mechatronics engineers, whatever. We all use these on a daily basis, all right? And essentially it enables us to rapidly prototype. So we can add components to this, we can remove components, we can remove them all completely. Essentially, it stops us from having to solder these things up, which are essentially prototype boards, we call them. So it removes the need to have to solder components together and that sort of thing. Okay. While you're all completing that step, what I'll do, I'll just have a little word on how we navigate the workspace, if you're not already familiar with it. To zoom in, you use your scroll wheel to move it forward to zoom in, move it backwards to zoom out. If you're using your laptop trackpad, gesture control, open your fingers to, sorry, 2-finger gesture control, open your fingers to zoom in, close your fingers to zoom out, okay? To move the entire workpiece, if you just move your mouse cursor away from all of the components, left click and hold, and then just move your mouse around, and the same with the trackpad, just move your finger around. If you just want to move one component on its own, you just left click on the component and hold, and then just move it around using your mouse or the trackpad again. Okay. Is everyone okay with that? Are we all ready to move on?
Yes.
Excellent, good stuff. Okay, so again, first thing that we always do, we power our components. Okay, so if you have a look just on the bottom row of pins on the Arduino, you will see the 5-volt pin. We're going to click on that, and we're going to move it over to the positive terminal on the bottom of the breadboard, or the bottom half of the breadboard, and we're going to change that wire color to red. Can anyone remember why we're changing this wire color to red? If you've took one of the classes before, can anyone remember why we changed them to red? Anyone? No?
It's like an international convention.
Brilliant. Okay. And positives are always red. Black is always black. Sorry, black is always black. Negative is always black. Excuse me. Yes, that's the convention, and we must always stick to this. All right. And that's not because using a different wire color will affect the operation of the system. It will not. It's for safety reasons. Okay. It's so if someone comes along after we've actually installed something, and they come along and they start trying to work on the system itself, if we don't identify which wires are carrying the load or carrying the power, they've got potential of really seriously harming themselves. Okay, not really. Well, I was going to say not really with this system, but that's not entirely true. Okay, are you all familiar with square 9-volt batteries? Okay, actually 3 people a year pass away from putting their tongue on the square batteries. So this system can and will cause you harm as well. Okay, so safety first, people. Right, the next thing we're going to do, we're going to power the top half of the breadboard. So again, on the positive terminal on the bottom side, bottom of the breadboard, bottom left hand. I'll get my words out properly in a minute. From the bottom of the breadboard, we click on the positive terminal, and we move that over to the positive terminal on the top half of the breadboard, and we're going to change that color to red. And again, we're going to add our bend points. Sorry for those who haven't actually attended one of these classes before. I will just explain to you how to actually create a bend point. We hover over the wire, just double click on the wire itself, a round circle will appear, and then you can just left click and drag that bend point any which way you would like. Okay, and there we go. Okay, we're going to repeat that step for the negative, just like that, and we're going to change that wire color to black because it's a negative. Okay, and we're going to add our bend points again, just like that. Quick okay for, are we ready to move on? Are we okay? Or was that very quick?
Go ahead.
Excellent.
Yes.
Good stuff. Excellent. Thank you very much. Okay. So in our component search bar again, we're going to add something called a potentiometer. All right. It should be when the search bar is blank, it should be just underneath. It's a basic component which we use all the time. Okay, and you will not even know where you're using these. You'll use them daily, more than once daily. Okay, and you won't know that you're actually using them. So it's just underneath the LED. Is that in the same place for everybody else? Can you all see a potentiometer? Anybody? Can you see a potentiometer in your component
Yes.
search bar? Yes,
Yes.
excellent. So, okay, so what we're going to do, we're going to click on that component, and we're going to move it over to the bottom half of the breadboard. Okay, just keep it in the same orientation. Okay, right. So while you're doing that, I'll just explain what a potentiometer is. A potentiometer, essentially, you can think of it as a variable resistor. Okay, so what a variable resistor does, it essentially just the resistance is variable. Okay, so you can have no resistance whatsoever right the way through. What's the rating on this one? Right the way through to this one's rated at 250k ohms. Okay, or 250,000 ohms. So as I'm sure you'll all be familiar with, electricity will follow the path of least resistance. All right. So if you increase the resistance on this, it will it actually forms what's called a potential divider. And what happens is the more the resistance is, the less potential or the less voltage levels will be released from the sensor on the signal wire. Okay, and then the more the resistance, the less potential will flow through the resistor. Sorry, I hope that was clear. Okay, because it didn't really sound clear with me when I was actually saying it in my head. Okay.
Sorry, Professor, can you just show again where you can find the potentiometer, please?
Yes, I will do. So in your component search bar, if you just delete everything in your component search bar, so it's essentially a basic component. So it should just you should just have if you look at my screen now, you should just have a list of basic components there. Okay, and potentiometer is on the right hand side, the second one down. Okay, have you found it?
Yes.
Yes, excellent. Good. Okay, so again, I've just explained what how the potentiometer works, and where I was saying you use these continuously all day long, every time you turn, let's say for instance, your higher and lower volume on a stereo system if you have them. I might be showing my age a little bit there. Okay, so every time you turn something on an electrical equipment, that could be your microwave, where you actually increase the time on your microwave. Anything that you do, turn a knob on an electronic component, that is a potentiometer. Okay, and that potentiometer basically just sends a signal to the controller and alters whatever it needs to alter. Okay, so you use these all the time, and they're the basic components. So first thing that we're going to do, I bet you can't guess what the first thing we're going to do. We're going to power the component. Okay, so on terminal 1, let me just pull my PDF on to make sure that terminal 1, we're going to connect this to the negative side on the breadboard, just like that, and we're going to change that wire color to black because it's a negative. The next one we're going to connect up is on the far right pin, which is the terminal 2, and we're just going to connect that up to the positive on the breadboard, or the positive rail, or buzz bar they call them, and we're going to change that color to red. Interestingly, you could connect the right hand side to the negative, and the other way around as well, and the opposite way around. Essentially, all it does is it alters. So if this is at 0 volts now, okay. If you swap this over, it would actually be at max volts. Okay, it just alters which way it actually works. So no big deal there. Okay. Is everyone okay with that?
Yep.
Yeah, excellent. Okay, so the next thing that we're going to do, we're going to add the signal cable, or the wiper, sorry. This is going to be connected to the Arduino itself, and this is going to input the different signal value to the Arduino. Excuse me. So we're going to connect that to A0 on the bottom row of pins on the Arduino. The reason we're connecting this to an AO pin or an A pin, it's because it's an analog signal. Okay, the other side are digital signals. This side's an analog signal. Okay, are any of you familiar with the difference between analog and digital? Anybody? Just say no if you're not.
No.
Oh, okay. Analog, essentially, I won't go into it too far because it can be quite confusing. Analog, we live in an analog world, okay? And essentially what analog is, it means it's a continuous signal, okay? It doesn't stop. It's got an infinite amount of values, all right? A digital signal has got a limited amount of values, or discrete. It's discrete values, okay? So it's got values of either, for example, between 0 and 20, okay? And it can only have values between 0 and 20. If it's an analog signal, again, it can have bounds where it's in between 0 and 20, but it can be any value at all in between that to infinity, okay? That's the difference between analog and digital, right? So this potentiometer, what we're actually going to be using this potentiometer for in this demonstration, it's actually going to simulate or a throttle or gas pedal, if you want to call it that, in a car, okay? So essentially many cars, or many modern cars today, are what we call drive-by-wire, okay? And that essentially means it's driven by an electrical signal along a wire. That's why they call it drive-by-wire. And that does use a potentiometer to send them signals. So if you're in a car that's drive-by-wire, when you push the gas pedal or throttle or accelerator, whatever you want to call it, it's actually altering the resistance on a potentiometer, which sends a different signal level to the controller. And I'll explain a little bit further on how it actually works in the engine. Okay, is everyone okay with that?
Sorry, Professor. Can you repeat the last step, please?
Yes, I sure can. Okay, so do you want me to repeat where the signal wire is going to be connected, or do you want me to just explain how to connect the potentiometer? Tell you what I'll do. I'll just explain how to connect the potentiometer again. It's no big deal. Okay, so I'll delete them wires. This is another, if you actually connect the wire up wrong, if you just highlight the wire and just click delete, okay? Just like that, right? So the first one we're going to do, we're going to power the potentiometer. So the very left-hand terminal, or terminal 1 on the potentiometer, if we just click on that, we're going to drag that down to the negative on the bottom side of the breadboard. And we'll again change the wire code to black. Then the far right pin on the potentiometer, or terminal 2, we're going to click on that and we're going to drag that down to the positive terminal on the bottom half of the breadboard. And again, we're going to change that wire code to red. And then we're going to connect it up to the Arduino itself. Okay, so that's the center pin, or the wiper, or the signal pin. If we just click on that, and we're going to connect that to A0, which is on the bottom side of the Arduino. Again, if you just hover over each one of these pins, it will actually identify what it is. So you're looking for A0. All right. Is that okay? Are we all right?
Okay, thank you.
Excellent,
Sorry, Professor, but
yeah?
could you just zoom in a little bit, please?
Yeah, of course. Sure can. There we go. Just like that.
Thank you.
No problem at all. Okay. Again, you just tell me when you're ready. You just say okay, and I'll move on. Are we all okay?
Okay.
Excellent. Good. Right. So I'll move on. Right. The next thing that we're going to add is something called a servo motor. Let's see if I can get one. I've got one here somewhere. I should have one. There we go. I've got loads of them. Okay. This is actually a servo motor. Okay. This thing here, if you can see on my screen, this is a servo motor. Right. You will be familiar with them again, even if you don't know you're familiar with them. Okay. I'm trying to think of where you'd actually see a servo motor now. So remote control cars. Okay, if any of you got any toy cars or anything like that, RC cars, when you see the wheels turning, just like that, when you signal on your controller, that's a servo motor. Okay, so servo motors, they're not like ordinary DC motors like this. Okay, because they can only actually move from 0 to 180 degrees. They cannot run. full rotation, full 360 degrees. If they do, or you ever do run them at 360 degrees, they will explode. Okay, the gears inside them will just disintegrate. Believe me, I've done it. Okay, right. So to add the servo motor, if we just in the component search bar on the right hand side, if we type in servo, I forgot to spell servo, SERVO, right? Okay, and that may be different in Portuguese. Can someone help me out with servo?
It's the same.
Yeah, I think it's
Is it the same? Brilliant. Okay, so just underneath, you will see something called a micro servo. It doesn't really matter with this because we're only going to be using the servo to simulate what a throttle body is. I know you won't all be familiar with throttle body and what it actually is, but essentially it's what's in the engine that makes the car go faster. Okay, so the more the throttle body opens, the faster the car goes. The less it opens, the slower the car goes. Essentially, that's exactly how it works. Okay. So once you've actually added the servo motor or the throttle body, as we're going to be calling it today, what we're going to do, we're going to alter the orientation of the servo motor. It just makes it the design look a little bit neater and makes it easier to connect it up. So again, on the top left-hand corner, you will see a button called rotate. It's right next to the trash can. It looks like a little mountain with a curved arrow on it. If we just keep clicking that till the servo is orientated just like that. Okay. You just let me know when you're ready to continue. Just a quick okay.
Okay.
Brilliant. Excellent. Okay. Is anybody having any problems before we move on?
Prefecture.
Yeah?
Just hold just a minute.
Yeah, no problem. You let me know when you're ready to go. Okay? We're zipping through this really, really quickly, so don't worry about the time. So while we're waiting a second, are we all really, really, really interested in Arduino now? I hope so. Anybody? Anyone thinking about buying a kit?
Yeah, I really like it, but my website is not loading, so I can. I'm just following.
Oh no, nightmare! Yeah, Tinkercad is not without its
But I
issues.
really like it. I have some friends that have some.
Really?
Yeah, they really like it.
Did you attend the robotics class by any chance?
Wait, sorry?
Did you attend the robotics class that we run?
Oh no, I didn't. It was already
Did you
full,
not?
and I tried to go.
Ah, was it? Right,
Yeah.
okay. Well, what I've got a guide on how you can actually build one of these. Okay.
Oh, actually, that sounds.
Yeah. So what I'll do, in fact, can I share that document now?
Oh, I wish. That
Let
looks
me
nice.
Let me see if I can share that document now. Oh no, we had issues uploading. Tell you what we'll do. Yeah.
Sorry, Professor. If you want to send to me, so I can forward to this gentleman.
I will do.
Thanks.
Well, what I'll do as soon as I've finished, we finished this webinar, I'll email it over because there's a file with code in it as well. So essentially, once you get your Arduino, you're just ready to upload it to the Arduino or burn it to the Arduino. So, and there's a couple of little things, experiments that I've actually built into it. So things for you to try. So it actually includes servos as well. So this will be.
Alright, that's nice. I just need to find the parts to buy.
Well, I've actually included a link on where to buy them as well.
Oh, actually, okay, that's great.
Excellent. So it's an international link as well. So it's a company called Banggood.
Oh yeah, I know.
You know
Okay,
Banggood,
that's
yeah.
great, thanks.
Yeah. It's a Chinese company. Really, really cheap components. That's where I buy all of my components.
Okay, thanks.
No problem at all.
Professor,
Yes.
Can you send me also, please?
Yes, I will do. I will do, definitely. If you just what I'll do, I'll send it to Diego. If you let Diego know, whoever wants it, and he will send it to you all. Or better still, if you well, not better still, if you would like to email me, no problem at all. I'll just send it straight out to you. It's no big deal.
Okay, thank you.
Yeah, no problem. I've just realised I've left a brand on top of the on top of the PDF with leads on it. Just ignore that for me, please. I shouldn't have done that. Okay, are we everyone okay? Are we ready to go?
Yes.
Okay, Professor.
Brilliant. Okay. Right. Okay. So I bet you can't guess what the first thing we're going to do. We're going to power the component. Okay. So to power the component, again, if you hover over each one of the pins on the servo itself, it will actually identify what it is. So you've got ground at the bottom, in the middle, you've got power, and then you've got a signal cable at the very top. Okay, I'll talk a little bit more about how the servos work in a second, and more specifically what signals you get from the Arduino. Okay, so the first thing we're going to do, we're going to connect up the ground. Okay, so we click on the ground on the servo, and we're going to connect that to the negative terminal on the breadboard. And again, we're going to change that to black because it's the negative. All right, and then add our bend points. Just like that. Okay. And then we're going to connect up the positive, which is in the center. So we click on power, and then we move that over to the positive side on the breadboard. And we're going to change that to red because it's a positive. Just like that. Okay. Again, just a quick okay when you have done that. When you have done that, sorry, not when you have done that. Just again, the Liverpool coming out of me there.
Okay, Professor.
Excellent, good, brilliant, brilliant. Okay, so the last one we're going to do, we're going to actually connect the servo signal wire to the Arduino itself. Okay, so let me just drop that down slightly so it doesn't cross it. Okay, so we click on the signal wire, and we're going to connect this to, I think it's, digital pin 9, okay? So we're going to connect this to digital pin 9, and we'll change the wire color on this to, we'll just change it to orange. Okay, and again, we're going to add our bend points. Right. You will see on, let me just move that out of the way. You will see on the pin that we're connecting it to, you will see like a little wavy line, okay, just before the number itself. What this does, this indicates that it's a pin that we can use pulse width modulation on. I know that's it sounds really, really confusing because it is. All right, so I won't go into it too far because it can be a little bit complicated. So what pulse width modulation essentially is, as we've already explained, well, I may have already explained, the Arduino is a purely digital system. Okay, so we need some way of turning this digital signal, which is either a high or a low, a 1 or a 0. Okay, we need a way of changing this signal into a analog signal. Okay, and we do this using pulse width modulation. Okay, if you're interested in learning a little bit more about pulse width modulation, again, I've wrote a tutorial for you. All right, it's quite a long tutorial. All right, but don't be scared away by it. What I've actually done, I've backed up the theory side of it with experiments that you can actually perform within Tinkercad as well. So if you're interested in that, again, let me know and I'll send it straight over to you. Okay. Right, is everyone okay with that?
Okay, okay.
Excellent, good stuff, brilliant. Okay, so the next thing that we're going to add, we're going to add our friend, the ultrasonic distance sensor. Okay, this is not what an automatic braking system in a car would use. It is not what it would use. It would use something called LiDAR, okay, which is essentially a laser distance sensor. That's why it's called a LiDAR, okay. So LiDAR systems, sorry, are much more accurate and much more reliable than the ultrasonic or um, sonar systems. Much more accurate and much more stable. But unfortunately, within Tinkercad, it doesn't actually give us a LiDAR component. So this will act as it, and it will perform the same task as the LiDAR, but in reality, it does not. A car braking system will not use it. Okay, so to add the ultrasonic distance sensor, if we just add type in the component search bar on the right hand side, ultra, ULTRA, okay, and you'll see again, this might not be the same in Portuguese. Could one of you give me a hand with that?
Sensor de distância.
There we go. Excellent. Thank you very much. And again, for those of you who did the robotics class, do not use the top one, which is a 3-pin. Use the 4-pin at the bottom. Okay. And we're just going to move that, and we're going to move it here, just like that. Okay. And again, just let me know when you're ready to continue on that. This is virtually it now. We've virtually completed the mechatronic system. Okay. Obviously, the system in a car is slightly more complicated than this, or slightly more in depth with this. It actually uses a really simplified artificial intelligence as well. Okay, and it uses that just basically to gauge, not gauge the distance, it uses the sensor to gauge the distance, but it actually feeds that sensory input into an artificial intelligence system, which will predict if a car's going to brake suddenly, or when it brakes suddenly, it stops it and that sort of thing. So again, it's just not a simplified version, but it's an ideal example. It demonstrates exactly how they work. Okay. Is everyone okay? Yeah.
Yes.
Yeah. Sorry, I'm going to ask that question. Are you all familiar with automatic braking systems? Have you seen them in use? Or are you familiar with them in any way?
There's no much Tesla cars here in Brazil.
Exactly. Right. Okay. Well, they're actually. It was actually Volvo who pioneered automatic braking systems. Yeah, they pioneered it. Again, have a little look on YouTube, because this video isn't going to work. I've tried to click and get it working, but it's not. But have a little look on YouTube about our automatic braking systems. It's really fascinating, to be honest, how they work. But they're not without their issues, and you will see that in the video. Okay. Right. Okay. So I think everyone's okay. Right. The first thing again, we're going to power the component. Okay, so on the left hand side, the left hand pin, you will see a VCC, and when you hover over the pin, it will say power. Again, VCC is just another symbol for power. Okay, what we're going to do, we're going to click on that power pin, and then we're going to drag that down to the positive terminal on the breadboard, and again, we're going to change that to red, and I'm going to straighten that up because again, I'm OCD about straight lines. There we go. And then the next thing we're going to do, we're going to connect up the ground pin, which is the far right hand side pin, just like that. And we're going to change that to black. Okay. While you're doing that, for those of you who are not familiar with the ultrasonic distance sensor, I'll just explain briefly how they work. Okay. You'll see an opening on the left hand side. That's essentially a speaker. Okay. What happens is it gets a signal from the Arduino, which triggers a sound wave or a sound pulse. That sound pulse then travels out to an object, bounces off the object, returns to the right-hand opening, which is essentially a microphone. That microphone, once that's received by the microphone, the sensor will send a signal to the Arduino. The Arduino will then, basically gauges how long it took, or the pulse duration, how long it took the pulse to go to the object and back again. We will divide that pulse duration in two, because you only want the distance to the object, not to and from the object. And then it's a simple equation then, which is speed is distance over time, therefore distance is speed multiplied by time, and that gives you your distance. Okay, and obviously the speed in this will be the speed of sound. Okay, the speed factor will be the speed of sound. Right? Okay, is everyone okay with that? We ready to go?
Yes.
Yes, okay.
Brilliant. Okay, so what we're going to do, we're going to connect. I'm going to connect the sensor to the Arduino itself. Okay, so the trigger pin goes to pin 13, just like that. Digital pin 13, sorry, which is on the top row of pins on the Arduino. Okay, we're going to change that color to whatever color you want. Let's change it to yellow this time. Okay, and then we're going to add our bend points. Keep it nice and neat. Keep it nice and neat and make it easier to trace any problems. Okay, and then the next one, the final remaining pin, we're going to connect that to digital pin 12. Just like that. Okay, and we'll change that. We'll change it to blue, just because I like blue. There we go. Just like that. Okay, is everyone okay with that?
Yes.
Excellent. Okay, so that's it. Essentially, you've built your first mechatronic system. So, where in this would you say is mechanical? Can anyone have a little guess on which parts of these are mechanical? Because it's got to have a mechanical element to be a mechatronic system. So, which parts of these would you say were mechanical?
The servo and the distance sensor.
Not the distance sensor. Well, no. Sorry. No, you are right.
Yeah, it's ultrasonic.
Yeah, that's it. Well, you've got essentially what you've got. The speaker itself is a mechatronic system, because that sends an electrical signal into a mechanical. Basically, it makes the speaker vibrate, which is a mechanical force. Okay, and then also the microphone. So the microphone itself will have a film or some sort of like plastic film, if you like. It's not actually plastic, but what happens is when that receives the pulse, that film will vibrate like that, and that will then in turn generate an electrical signal. So yes, you're totally right. And yes, the servo is a mechanical system. If I zoom in on the servo, you will see some gearing inside it. Okay, again, mechanical. One that you may not actually think of is the potentiometer. The potentiometer, or in this case, the throttle or the electronic throttle, it's a mechanical element. It transforms a mechanical force. So it won't actually let me do it until I start the simulation. But see this, you'll see like the black stripe there. That just indicates where the actual potentiometer is at that time. When I actually physically move that, that's turning mechanical force into an electrical signal. Okay, so that's a mechatronic system, and that's the same in a car. Once you put your foot on the accelerator or foot on the gas pedal, that's a mechanical force, and that you're transferring a mechanical force into into an electrical signal, mechatronic system. Okay, right. So now what we're going to do, we're going to move into the code. Okay, so for those of you who aren't familiar with this side, if you have a look at the top right hand corner, you will see 4 buttons. Okay, the very end button says code. We're going to click on code just like that. Okay, again, you're faced with block code or what's called Scratch. Okay, we're not going to be using this today, and I recommend that none of you use it in the future. If you're going to have a little go at Arduino, use text, all right, and it'll set you up massively for your academic careers and your professional careers if you move into something along these lines. Okay, so we're going to click text. Sorry, let me just repeat that step. In the top, once the coding workspace is opened, you will see a drop-down box with blocks in it. You just click blocks. Just beneath that, you've got text. Okay, click text, and then an alert box will come up. If you just click continue on that, okay, and you will see the text representation of the block code you have just seen. Is everyone okay with that? Have we managed to do that? Oh. Right, sorry, I've forgotten elements. I forgot the most important part. I forgot the actual break. Okay, the break. Right. So what we're going to do, I do apologize, everybody. Let's close that coding workspace. Right, what we're going to add, if we just delete everything out of your compelling search box, you will see an LED. All right. The LED, an LED is what we're going to be using an LED for. Obviously, you're all familiar with LEDs. They're basically a light emitting diode. So once they have current running through them, they will light up. Okay. So we're going to add the LED. By clicking the LED, we're going to move that over to the breadboard, just like that. Okay. Interestingly, with diodes, or this is a light emitting diode, but any diode will only conduct in one direction from from cathode to anode. Okay, cathode negative, anode positive. All right, they will only conduct in one direction. All right. If you've all seen the rectifier circuits, like I explained earlier, they use diodes, okay, because they will only conduct in one direction and one direction only. All right. Has everybody added the LED? I do apologize for missing this step. Is everyone okay if we added the LED?
Okay.
Yes, excellent. Okay. So what we're going to do, we're going to connect the cathode. If we hover over it like that, the cathode is going to be connected to the negative on the breadboard, and we're going to change that wire code to black. Okay. And then we're going to connect the anode, or the positive, which is on the right hand side. We're going to connect that to digital pin 2 on the Arduino, just there on the top side of the Arduino. We're going to change that to we'll change that to pink. Okay, just like that, and then we'll add our bend points. Again, I do apologize for missing this step. It's probably the most important step. So again, what we're going to actually use, we're going to use this LED as to simulate the braking system. Okay, so the braking system in a modern day car will have its own microcontroller or central microcontroller or processing unit, microprocessing unit. I can't get my words out today, I apologize. So it'll either have one of these or one of them, and that will look after the things like ABS, the ABS aids, which stop your wheels from locking up and stop you from skidding along. So basically it allows you to brake in a controlled manner. So that will look after that sort of thing. It will also look after, it'll have elements of the traction control as well. So you may brake slightly to stop your wheels from spinning and that sort of thing. Okay. Has everyone done that? Is everyone okay with that?
Yes.
Excellent. Okay. So now we're going to do the code side again. All right. So we're already on the text code. Is everybody okay? Is everybody up to this stage with the coding side?
Professor, in the tutorial has a resistor and you didn't add
Yes.
it.
Yes, very, very good. Very, very good. Okay, I haven't added it to this because it doesn't really matter too much with this. Okay, what the resistor is there for, though, if you are powering, if you are using resistors in real life, say for example, you're attaching one to an Arduino like that. Okay, if you don't use that resistor, essentially is called a current limiting resistor. Okay, if you don't use a current limiting resistor, excuse me, when you're powering an LED, they will literally burst into flames, or eventually will burst into flames. It's because the current is way too high for the resistor. So that's why, sorry, for the LED or the diode. That's why you use a resistor there. But well done for noticing that. Well done for noticing that. Okay, it's not massively important with this, but what I will show you when we start the simulation, I'll show you what it says. Okay, it basically says put an LED, put a resistor there, otherwise it's going to burst into flames. Right. Okay, are we all ready? Are we all ready to move on to the coding side?
Yes.
Excellent. Good, 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 good. Okay, so what we're going to do, we're going to delete this text code. That's already present in the window. And what we're going to do, just underneath the last where you actually add the LED in your PDF, you will see add the code. Step 5, add the code. Okay, and the first block of code, or the first text box with code in it, is where we declare and initialize our variables, and also add any libraries that we're going to use. Okay, I'll explain a little bit more about that when while I'm waiting for you to actually add the code. So what we're going to do, we're going to copy that block of code, and we're going to paste that into the coding window. And of course, right, this is an issue. If you what's happened here, have you all opened the PDF in your browser rather than a PDF reader? Okay, if you open it in a PDF reader, this is what happens. All right, so I'm going to delete that code. I'm now going to open it in my browser instead. Okay, just 1 second. Have you all opened it in a browser? Anybody? Anybody there?
Yes.
Yeah, okay. So you've done a better job than me then. Brilliant. Much better than me. See, we all make mistakes, okay? Mistakes are not a bad thing. They're actually a really, really, really positive thing. So make as many mistakes as you possibly can. It's the only time you actually learn anything, okay? So again, I'll just copy this block of code, the first block of code in there, okay? And I'll explain a little bit about what this is, okay? Right, you will see at the top, all right. An Arduino sketch has got a minimum of 3 sections with an optional 4th section. Okay. So the 3 sections, the 3 mandatory sections within an Arduino sketch. The first section, you declare or you include any libraries you're going to use. A library is essentially an object. We're going into the realms of object-oriented programming here, but it's essentially a block of code that some kind person has already written for us. Okay, in this case, it's to drive the servo. Okay, because the servo uses pulse width modulation. This actual library handles pulse width modulation for us. Okay, so the next thing you will see, the next line of code you will see servo and then T-body. Okay, what this is, again, don't worry about this too much. What this does, it declares a new instance of the servo object. Okay, I know that sounds really complicated, but it's massively important that you do that. Okay, you need to declare a new instance of the object. This you can actually do many times. For example, with this, I've got 6 servos. Okay, so you can actually do this 6 times and declare 6 different servos, right? Okay, so the next line of code, the sensor value. So that's the potentiometer. So that's the value that comes from this potentiometer. That's going to be a value of anything between 1,000 and 1,023. Sorry, 0 and 1,023. Okay, and that is basically because the Arduino itself has got, if you remember what I said about analog and digital sensors or analog and digital signals, the potentiometer is an analog signal. Okay, so therefore the Arduino has got to transform that analog signal to a digital signal so it can actually read it. Okay, and it uses something called an ADC, or an analog to digital converter. All right, and in the case of the Arduino, it's a 10-bit analog to, or it's got a 10-bit resolution analog to digital converter, which basically means 2 to the power of 10 is 1,024. So therefore, it's got a range of 0 to 1,023 with a possible amount of values of 1,024. There you go. Again, another mouthful, but you'd actually learn something there. Right. Okay. Are we all okay? Did we all manage to do that?
Yes.
Yes, Professor.
Excellent. Okay. So the next block of code we're going to add is the setup routine, or void setup. Okay. So we're going to copy that and we're going to add that to our block of code, just like that. Okay. And while we're doing this, I'll just explain to you a little bit about what this actually does. So, okay, so for those who didn't do the robotics, oh, sorry, I've got a bit of solder. For those of you who didn't do the robotics or didn't attend the robotics class, the setup routine is essentially just what you use. It's where you tell the Arduino what you want to do with the pins that you've attached components to. Okay, so you will see at the top in this routine, you'll see T body or throttle body dot attach. Okay, 9. So this is a function within the servo library, or within the servo object, that that essentially attaches that servo to. Right, I've just noticed a mistake. I've actually attached my servo to digital pin 10. Okay, isn't that good? Right, so that wouldn't have worked, would it? For some reason, it's going absolutely nuts. Just 1 second. There we go. So I'm just going to move that to digital pin 9. Just like that. Okay. There we go. Right, I'll open the code again. So as you can see, a T-body dot attach. So that attaches the servo, the T-body or the throttle body servo, to digital pin 9. That's exactly all that does. Then you've got pin mode, A0 as an input. So you're declaring the analog pin that the sensor is attached to. So analog 0. Okay, and we're declaring as an input because it is an input. You're actually taking a signal from the sensor and inputting it into the Arduino itself. Trigger pin on the trigger pin. Sorry, the Arduino sends a signal from the Arduino to the sensor, so it's an output. And then the echo pin sends a signal from the sensor to the Arduino, so therefore it's an input. Okay, and then you've got pin mode 2, number 2 output. That's just the sensor. Sorry, the LED. Okay, is everyone okay with that? Should we move on?
Yes, yes.
Excellent. Okay, so the next thing that we're going to do, we're going to add the loop routine. And the loop routine essentially does exactly what it says. It just continuously runs. So you will see the first 2 sections, they will only ever run once. on an Arduino, okay? And the loop section, as long as the Arduino's got power, it will loop and continuously loop, all right? So while we're doing that, while you're doing that, the indentation has gone nuts on this, so it doesn't really matter too much. Okay, right, so the first line of code in the loop routine, you'll see find distance. Again, if you attended the robotics class, you will know what this is. Okay, essentially what this does, it takes it runs the ultrasonic sensor, distance sensor, sorry, and then what that will do, that will return a distance. Okay, have I got distance here? Yes. Okay. If that distance is less than 10 centimeters, obviously this will be different in a car. Okay, it will be a variable distance depending on how fast you're going. Okay, obviously you've got braking distances. The faster you're going, the longer it takes you to stop. All right, so obviously this will be massively variable within an automatic braking system in a car, basically because the stopping distance is different, and it all depends on how fast the car in front of you is going as well. So massively complicated, so we won't go into it too much. Okay, if that distance is less than 10 centimeters, they say it will print, oh, an obstacle has been detected. This obstacle could be anything. Could be a car, it could be a cone in the middle of the road, it could be a pedestrian in the middle of the road. You do not know. Okay, that will then, because there's an obstacle being detected, it will move the throttle body to 0. So it will turn off or move, shut the throttle body off completely, which will stop the car accelerating in any way. It will then it will write or turn the LED on, which this simulates it engaging the braking system in the car. So this is exactly how it would work as well. It would actually just send the signal, a high 5 volts or a 1 to the braking system, and then the braking system would initialize, and then it will brake the car. That's exactly how it will work. There's no other way it will work. Okay. If the distance is anything else, it will disengage the brakes. Okay. It will then take a value from the sensor, from the potentiometer or the throttle itself, or the gas pedal, or the accelerator, whatever you want to call it. It will take a value from that. Okay. It will then map that sensor value. So it will map the value of between 0 and 1024 and 1023. It will map that signal, that value to between 0 and 180. Okay, as I've already explained, the servo can only traverse between 0 and 180. Okay, so that will map the signal from the sensor to the actual positioning of the Arduino, servo, right? And then it will write the that value to the servo. So, for example, if it's 80 degrees, it will move the throttle body servo to 80 degrees. Okay. And then the fourth and final, or the fourth and optional, we're going to add is the function to drive the ultrasonic distance sensor itself. Okay, so we're going to copy that over and we're going to paste it into our coding workspace, just like that. Okay, and again, the indentation's gone nuts, but don't worry about it. What does I mean by indentation? You should have an indent of 3 spaces within every routine. So, for example, within this routine, where you've said void find distance, you'd have an indentation of three spaces. Where you've got any sort of condition like an if or anything like that, then the code within that if would be indented by 3 spaces again. Okay, right? Is everybody okay with that? Have we all added all the code?
Yes.
Excellent.
Yes,
Okay.
Professor.
Brilliant. Oh, sorry, I've lost my screen. There it is. Okay. So what we're going to do now, we're going to simulate the system working. Okay. So what we're going to do, just at the very top, you will see something called Start Simulation. We just start this simulation. Please be no errors. Okay. So what we do, we just close this code workspace at the minute. Okay. So as you can see, if you just look at my screen now, and then you can have a little go at this as well. That little black line on the potentiometer itself, if you just left click and hold on that, and you can actually just turn that potentiometer, and then if you just look to the right, you will see the servo moving proportional to the distance that you've actually moved that the potentiometer. So obviously, in this configuration now, what's going on? Why is it moving? There we go. So for some reason, it's moving in the wrong direction, but it doesn't matter. Okay, so what I'll do, I'll move it back to 0. Okay. Is everybody else? No one's showing any errors. Is everyone okay? Anybody? Is everyone's servo moving? Anybody?
I have a question.
Yes, go for it, mate. Go for it.
Can a servo move? Can a servo move more than 360 degrees?
No.
Oh, no servo can do that. Okay.
No, you can actually buy servos. You can get servos that will move 360 degrees. But I don't understand why you'd actually use a servo for that. Because essentially, all it just turns into is a geared motor, just like that. And the geared motors are substantially cheaper than the servo motors.
Okay, thanks.
Is that all right? Another option for you, if you would like a little bit more control on the actual movements of the motor, because to control the movements on a DC motor, it's you can't use them for really precision tasks. You just simply can't. Another really valuable option would be something called a stepper motor. Okay, so if you need something that's really accurate but is enabled to move 360 degrees, use a stepper motor. Okay. Right. So has everybody actually got their servo moving?
Yes.
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 Okay. Again, brilliant. Okay. Again, Tinkercad is not without its issues. Okay. In reality, as soon as I move this, if it was basically a kit I just made with this, as soon as I move this this potentiometer or change the value of the resistance in this potentiometer, the servo would just literally zip around. Okay, it's really that quick. It's actually got a refresh rate of 60 hertz. Okay, or around about 60 times a second. Okay, so as I move it, it will just zip around. But again, Tinkercad hasn't quite got that refresh rate, so it's quite slow. All right, so the servo should be at its max now. Yeah, it is. So the servo is at its max. Okay, so that would basically mean the people who are driving the car have got their foot flat on the floor and they're going. Well, they're going like the clappers, as we say here. So they're going really, 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 really fast. All right. A pedestrian then stands in the middle of the road, or just an object appears in the middle of the road. So if we just click on that sensor, you will see a round circle. That's the pedestrian. That's the pedestrian, or that is an object, another car, a cone in the middle of the road, anything at all. Okay. If we move, the car will be moving towards this object. We wouldn't move the object towards it, but to simulate that, we'll move the object towards the sensor or towards the car, and then we've just moved it within 10 centimeters. Okay, you will see, if you look on my screen, you will see the servo or the throttle body moving to 0. Okay, and you will also see the LED light up, which basically means that the braking system has engaged. For the gent who had mentioned to me earlier about not putting a resistor on the LED, if you see that little bit of an extension, a little bit of an exclamation mark, if I just click on that, it basically says, why isn't it saying anything? There we go. It says, current through the LED is 5.5 milliamps, while recommended maximum is 20 milliamps. the usable lifetime of the LED may be reduced. That basically means if you use it for too long like this, it will burst into flames. Okay. Has everybody managed to get this moving, get it all simulated, and working?
Professor,
Yeah.
I think my simulation are not working because when I move one thing, the other don't move together. I don't know why.
It doesn't move together. Ah, right. So when you move the object closer to the sensor itself, so if I move it away from the sensor now, that LED should go off. There you go, yeah, so it's gone off. And then the throttle body will move to where the throttle is. Right, so I take it when you move the object, right, let me just pull that down a second. So if you just have a look at my screen now, when you move that object within 10 centimeters, just like that, what doesn't move? Does the servo not move?
Yes, I think yes, the servo that don't
Right.
move.
So is the servo moving when you move the potentiometer? So, sorry?
No, they are.
No.
Mm.
Right, okay. So have a little look. See the orange cable that's coming from the Arduino? Just make sure that's in digital pin 9 and not digital pin 10. Just have a little check at that now, because that's the mistake I made.
Okay.
Is that the
Is
the
it
problem?
in 9?
It's in 9.
Yes.
Yes, it should be in 9.
No, because. But this is not a problem. I don't
It's
know.
not a problem.
No.
Right. Okay. Okay. Right. So what I would do, when we finish this tutorial now, what I would do, I'd go through that PDF. Just go through each step and just double check all of your connections. Make sure all of your connections are right, all correct. Okay. And then go through the code and just make sure all the code is the same as well. Okay. It will work. I promise. I promise you it will work eventually. I promise. But this, again, honestly, this is the world of engineering. Honestly, you will make more mistakes and things will not work 99% of the time. It's only actually 1% of the time that they work. Okay, so get used to it. If you're going to be an engineer, get used to things not working. All right.
All right.
Yeah, everything that we develop, essentially what engineers are trying to do, engineers are trying to do the impossible on a daily basis. Okay. And if you're trying to do the impossible on a daily basis, expect to be disappointed on a daily basis because things won't work. All right. But again, it's a good thing. All right. So, some of the best discoveries have come through making mistakes. All right.
Okay, thanks.
No problem at all. Okay. So again, I hope everybody enjoyed that. And again, if you need, I will pass the PDF and the code onto Diego for to pass on to you about building the robot. If you've got anything else that you would like to ask me, or you want to contact me directly for it, please do so. Okay, it's not an issue, and I will send it to you myself. Okay, thank you very much. Diego, would you like to answer? Or has anybody got any questions for me before I finish? Anybody? Okay, don't worry about it. Don't worry about it at all. If you think of anything later on, or specifically for the person who is struggling getting this working, if you don't get it working, just let me know, and I'll sort it with you. I'll fix it with you. Okay.
Thank you very much, Professor. It was very clear class.
No problem at all.
Thank you very much. Was awesome. Thank you very much. Appreciate. Galera, então, aqueles que tenham alguma dúvida, manda um e-mail para mim que eu encaminho para o professor e ele está respondendo todo mundo direto depois. Aqueles que perguntaram sobre o extra tutorial, o professor Kroll vai me mandar e eu encaminho para aqueles que têm interesse, assim que ele me mandar. E eu quero convidar vocês hoje para a webinar que vai acontecer às 6 horas, daqui 1h20. Todos vocês já devem ter recebido aí o link para participar, mas quem não recebeu, manda um e-mail que eu passo o link aí para vocês se cadastrarem, para vocês assistirem. Vai ser bem bacana. Hoje vamos ter o Gustavo da Study Group falando sobre carreiras e graduação nos Estados Unidos. Vai ser uma conversa muito bacana. Ele vai falar sobre empregos aí do futuro, empregos que estão acontecendo lá fora, que aqui no Brasil, infelizmente, às vezes não tem muito reconhecimento. Bom, o professor Carl mandou e-mail ali, pode mandar e-mail para ele também. Bom, e é isso, galera. Eu espero que vocês tenham se divertido, espero que vocês tenham gostado muito, que essas mock classes estejam ajudando vocês aí no encontro da sua carreira. Vocês já estão na sua quarta, se eu não me engano, quarta aula de engenharia aí. Acho que já dá para ter uma noção qual engenharia vocês gostaram mais. Semana que vem tem mais 2, e aí depois eu falo da futura agenda de junho aí, tá bom? Muito obrigado, espero ver vocês hoje à noite no webinar, junto com o Gustavo, Efige e Study Group juntos. Obrigado, boa tarde.